All right, let's get right into it. We hear all the time about the incredible promise of quantum computing, right? But today, we're going to look at the other side of that coin. We're talking about a threat that isn't some far-off future problem. It's a danger to our entire digital world, and it's happening right now.
This quote right here, it really gets to the absolute heart of the issue. A silent, global heist is underway as we speak. Huge, vast amounts of our most sensitive data, we're talking everything from bank records to state secrets, are being siphoned off and stored away. So you gotta ask, why would anyone hoard data they can't even read? Well, the answer to that question is why we're here today.
It's a strategy called Store Now, Decrypt Later, or SNDL. And the idea is terrifyingly simple. You collect everything valuable that's locked up today, think industrial research, new drug formulas, military intelligence, and you just wait. The bet is that in a decade or two, a powerful enough quantum computer will exist that can crack today's encryption like it's nothing.
And look, this is not science fiction. This threat is so real, so imminent, that governments are already scrambling. The U.S. Congress isn't waiting around to see what happens. They've already passed laws mandating that every single federal agency starts upgrading to quantum-proof systems. Not next year, not next month, right now. The race has officially begun.
So, to really get why this is such a monumental deal, we first need to pull back the curtain on the digital locks that we all rely on every single day. The locks that, for the better part of 40 years, we honestly believed were unbreakable.
Before the 1970s, encryption was, well, kind of clunky. If you and I wanted to share a secret, we'd literally have to meet up in person to exchange a secret key. But then, in 1977, everything changed. Three guys, Rivest, Shamir, and Adelman, invented a system called RSA, and this brilliant idea of using public and private keys became the bedrock for the entire modern internet. The genius behind RSA is this really elegant mathematical trick. It works like this. You pick two massive prime numbers and you keep them totally secret. Then you multiply them together to get an even more gigantic number, and you can share that number with the whole world. That's your public key. Now, anyone can use your public number to lock a message, but, and this is the crucial part, only you, the person who knows those two original secret primes, can unlock it. 16 million years. Just let that sink in. That's how long it would take the most powerful supercomputer on Earth today to take that giant public number and figure out its two original prime factors. For a normal computer, it's just an impossibly hard math problem. And for decades, that made us feel pretty safe. It seemed totally unbreakable. Until it wasn't. And this is where our game changer enters the story, the quantum computer. See, this machine doesn't just think faster than a regular computer. It thinks in a completely different way, tapping into the bizarre, almost magical rules of quantum mechanics.
So here's where things get a little weird, but it's super important. Your laptop works with bits, which are either a 0 or a 1. Simple. But a quantum bit, or a qubit, can exist in what's called a superposition, meaning it can be both a 0 and 1 at the very same time. Because of this, its power grows exponentially. You add one more qubit, and you literally double your computing power.
Okay, get ready for a mind-bending fact. With just 300 stable qubits, a quantum computer could hold more possible values than there are atoms in the entire observable universe. I mean, the scale of that power is just, it's almost impossible to wrap your head around.
But, and this is a huge but, there's a catch. This massive parallel computation is incredibly fragile. The very moment you try to look at it to measure the answer, the whole superposition collapses. Poof! And you're left with just one single random value. All that other incredible information just vanishes. So for most jobs, this makes a quantum computer kind of useless.
But then, back in 1994, a mathematician named Peter Shor came up with an algorithm that is nothing short of genius. It brilliantly works around this measurement problem for one very specific task, factoring big numbers. See, Shor's algorithm doesn't try to find the answer directly. Instead, it finds a hidden rhythm, a repeating pattern in the math. It's that pattern, the periodicity, that holds the key.
So how does finding a pattern help? Well, let's walk through it with a simple number, like 77. The process involves doing a bunch of calculations and just looking at the remainders. The goal isn't the remainders themselves, but figuring out how many steps it takes for that sequence of remainders to start repeating. That number of steps, that's the period, R, and once you have that, finding the original factors is easy.
And you can see that pattern right here on the screen. The remainders seem totally random at first. 8, 64, 15, 15. But then, look, at step 11, The remainder is 8 again. It's the same as step 1. The whole pattern repeated itself after 10 steps. So the period R is 10. That's the magic number we were looking for.
Now, a classical computer would have to grind through this one step at a time, which for a huge encryption key would take, millions of years. But a quantum computer, it calculates all the remainders at once in that superposition. Then, Shor's algorithm does its magic, collapsing that superposition in just the right way to reveal that one special number, the period R. And once you have R, the game is over. The code is broken.
But you know what? Breaking our encryption is really just the beginning. The dawn of this quantum age brings a whole wave of geopolitical and societal risks that go way, way beyond your online banking password.
I mean, think about the ripple effect here. A quantum arms race could completely upend the global balance of power. The entire financial world of cryptocurrency and blockchain suddenly vulnerable. You could see AI supercharged for cyber warfare and disinformation like we've never seen before. It would create this massive quantum divide where nations without this tech are just left in the dust. Okay, so after all that doom and gloom, here's the good news. It's not a lost cause. Even as one team of geniuses is building the ultimate quantum key, another team is working just as hard to design a new generation of quantum proof locks.
The smartest people in the world have seen this coming for a while. Way back in 2016, the U.S. National Institute of Standards and Technology, or NIST, kicked off a global competition. They basically said, okay, everyone, we need a new way to do encryption. They got 82 proposals from all over the world, and after years of intense vetting, they finally picked the first batch of winners in 2022. And this new field has a name, Post-Quantum Cryptography, or PQC. The whole goal is to build our digital security on a completely new foundation, on math problems that are believed to be incredibly hard to solve for both regular computers and quantum computers.
One of the most promising ideas is called lattice cryptography, and the core concept is actually pretty cool. Imagine a perfectly ordered grid of points, like a lattice. If you have a nice, simple set of directions, your base vectors, finding any point on that grid is super easy. But now imagine you have a tangled, messy, chaotic set of directions that actually leads to the exact same grid. Finding a point now is almost impossible. The easy set of directions is the secret key. The messy, tangled set is the public key. So here's how you use it to send a secret message. You create your lattice with your good secret key, but you give everyone the hard public one. To send me a message, you find the point on the lattice that represents your data, and then you just nudge it a little bit, add some random noise. Now, for anyone with that hard key, finding the original point you started from is nearly impossible. But for me, with my easy secret key, I can instantly find the closest correct point on the grid and read your message. It's brilliant. So the solutions are here. They're being rolled out. But now comes the really, really hard part, actually using them. The big buzzword you're going to hear everywhere is quantum readiness. It means every company, every government, every organization needs to be figuring out what data is most critical and making a solid plan to switch over to these new standards. And they need to do it before it's too late. And that really brings us to the final, crucial question. The quantum future is coming, and it's coming fast. It holds both this unbelievable, revolutionary promise, but also this unprecedented level of danger. The technology itself isn't good or evil, but its impact? That's going to depend entirely on how well we prepare. So, are we ready?